This third example is going to take advantage of using forces that are easy to measure to determine forces that are a little bit harder to measure. It's a comparison of a force that you already know with magnetic force. And you'll see this come up quite often. This is the first unit we're using it, but you'll see us use it in many other instances throughout the course where you're comparing something to gravity to cause an object to be suspended. Now, back in the notes, you'll see that I give you some tips on dealing with a current balance. A current balance will have the magnetic force in one direction and the gravitational force in another direction. And if an object is going to be suspended, meaning levitate, then those two forces will be equal and opposite in a magnetic field. If it's going to accelerate upwards, then that's going to mean that the magnetic force is larger and it's going to accelerate upwards until it leaves the magnetic field, and then there will no longer be a force acting on it. If you want it to accelerate downward, then that means that the weight of the wire in the magnetic field is too heavy, so the magnetic force could no longer hold it up, and it'll fall as a result. So you can actually suspend lightweight wires if you run a current through them in a magnetic field. Now you need very strong magnets. It doesn't work with just regular fridge magnets, and you need really small, thin, light wires. Big magnetic fields, this is stuff you can't do with your typical type of fridge magnets. You need some big, powerful magnets, electromagnets, to make this happen, but you can levitate objects using magnetic fields and balancing and making that force oppose gravity. If you were to apply your left-hand rule, this picture, I have current going into the page, so my thumb is going into the page, my fingers are going from north to south. You should see that with your left hand that your palm is pointing upwards. Your force due to gravity is always down. So in this little experiment, to measure the strength of a magnetic field, which is hard to measure, there's no such thing as a magnetic field detector. You have to use a balancing of forces. So you use a current carrying rod with a mass of 31 grams and a length of 2.75 centimeters, really small, a line perpendicular to the magnetic field, and the wires are connected to a power supply. If the current is 5.1 amps, causing the rod to be suspended, what is the strength of the magnetic field? So if we start with suspended, then the first thing you have is that the magnetic force is equal to the force due to gravity. And we can use our formula for magnetic force. This is a current carrying conductor, so it's ILB equal to the force due to gravity, mg. We want the strength of the magnetic field, so the magnetic field will be mass times gravity divided by current times length. Notice the mass is easy to measure, gravity is known, constant, current is easy to measure with an ammeter, and the length is easy to measure. There's no such thing as a magnetic field measuring device, so you use other forces and balance formulas to determine magnetic field. So this would be a simple experiment that you could do in a classroom to see how strong a magnetic field would be. And if we put our numbers in, the mass in this case was 31 grams, so it's 0.0310 kilograms. Masses have to be in kilograms. Gravity 9.81 newtons per kilogram divided by the current 5.10 amps times the length, which was given to us as 2.75 centimeters. So I'm going to write this as 2.75 times 10 to the negative 2 meters. Make sure you have everything in the right units. Punch this in, 0.031 times 9.81, divide by bracket 5.1, 2.75 to the exponent negative 2, and you should get a magnetic field strength of 2.17 Tesla. That is very, very powerful. Bar magnets were in the neighborhood of 10 to the negative 3, 10 to the negative 2, 10 to the negative 4. So when you get something 2 Teslas, that's very powerful magnetic fields. Not something you buy at a little fridge magnet in this case. So what you have to look for in your questions is whether the object is suspended. Then you quickly just balance the forces, and then if it's being accelerated either up or down, then you start with the larger force to find net force. And you know net force can be written as MA, so you could figure out the acceleration up or down by starting with your balancing of forces, something you've done back in Unit 1. So you can use these formulas to figure out how fast it'll accelerate up, or how fast, or I shouldn't say how fast, the rate of acceleration upward, or the rate of acceleration downward, depending on what you're given in the problem.